even in our daily life, it happens under this condition called transient or unsteady state. Okay, so give you an example. So in steady state, like I mentioned before, right, in steady state, for example, we want to study, say, many layers. Okay, we want to calculate the heat transfer rate from point number 1 to point number 2. Okay, and the basic assumption is temperature at point number 1, T1. Now let's assume T1 is greater than T2. So we know the heat will be transferred from point 1 to point 2. Okay. So and when we say we assume the system is under steady state, it means the temperature at point number 1 is maintained at T1, and temperature at point number 2 is also maintained at T2. So the temperature doesn't change over time. The temperature at any point in the system, okay, let's say you have a point here. Okay, this is point number 3. It is at T3. So when we say the system is under steady state, it means we use certain way in maintaining the temperatures at any point in the system at constant over time. Okay, the temperature at any point is set as constant over time. It doesn't change over time. Okay, so how do we do that in industry? Very easy. If this is, let's say, a block, right, in the industry. So normally what we do, why the temperature is higher than here? So it could be there is maybe a heating, there is a source of heat provided, right? A source of heat provided to this end. Maybe there could also be this here at point number 2, or surface number 2. Okay, there will also be a source of heat, right? Surface number 2. Here we have surface number 1. So maybe there are source of heat. Okay, meaning you use heating, right? So that heat is constantly supplied to the point, to both points or to one of the points. Okay, so that the temperature at any point in the system can be maintained at that temperature. Okay, this is what we say if the system is under steady state. Okay, but what about transient? Okay, transient is opposite. It means the temperature. When we talk about heat transfer, it means temperature. Okay, if you talk about mass transfer, then what we mean is concentration or partial pressure. If some gas system, so we use partial pressure. Okay, temperature and heat flux at any given point in the system changes with time. This is under transient. Or if we say the system involves mass transfer, it means concentration or partial pressure and mass flux at any given point in the system changes with time. So if we can't see the same system again, right? So if we say this system is transient or unsteady state, so it means initially when t equals to 0, when we start counting the time, the t is at t1. But when T is at maybe 2 seconds, right? Because there is no heat supply to this point, okay, or more heat is supplied when you set T0, when you start your stopwatch, right? The heat supply changes, right, suddenly. Then what will happen is, then the temperature at point number 1, at point number 3, over time changes as well. Yeah. So this is what it means. And because temperature change, then the Q also change, heat flux. The same goes to mass transfer, concentration or partial pressure, and mass flux. Okay, a typical example is, let's consider a heated object, okay, is removed from a furnace. Right? Let's say this is the object, right? The object. Uh, it is removed from a furnace, okay, then exposed to a cold stream or surrounding, right? So this object taken out from a furnace, okay, at time when we take it out from the furnace, then we start the stopwatch, right? So when we start the stopwatch, T equals to 0. So at that point, temperature of the object is at 150 degrees Celsius. Okay, but because no heat is supplied to the object over time, so what will happen is over time temperature drops because the ambient temperature is 30 degrees Celsius. So heat will be transferred out, right, from the object to the surrounding. Then what will happen is when T equals to 1 minute, let's say, okay, then temperature drops maybe to 145 degrees Celsius. When T equals to 30 minutes, then T equals to maybe 100 degrees Celsius. Okay, so meaning temperature changes over time. Temperature of the body changes over time. So this is what we mean by unsteady state or transient. So let's see. So temperature of the body will decrease due to convection and radiation to the surrounding. So I'm talking about this object, right? Initially is 150 degrees Celsius. You see, the y-axis is temperature of the body. Then the x-axis is time in second. So initially when T equals to 0, okay, here is when T equals to 0, then temperature of the body is 150 degrees Celsius. And this is T ambient, right? 30 degrees Celsius. So over time, heat is lost to the surrounding through convection and radiation. Okay, then what will happen is temperature of the body drops over time, right? If the time is long enough, what will happen is it will reaches equilibrium, thermal equilibrium. Thermal equilibrium is a condition whereby the temperature of the body, okay, equals to temperature of the surrounding. TB equals to T infinity. So T infinity here is 30 degrees Celsius. So at the end, if the time is long enough, then the temperature of that object will become 30 degrees Celsius. Under this kind of situation, we say that the object is at thermal equilibrium with the surrounding. When thermal equilibrium is reached, it means there is no more heat transfer between the body and the surrounding because there is no temperature difference. Okay, so but what will happen if this object, let's say like inside this object there is something supply heat, right? So causing the temperature of the body maintain at 50 degrees Celsius. What will happen to this graph is over time, sorry, it's not straight. Actually, it's a straight line. So the temperature of the body will maintain at 150 degrees Celsius. This is steady state, right? This is steady state. So, and if it is transient, then the temperature of the body changes over time. Okay. So, and temperature distribution is dependent on the heat resistance in the body or conduction of the body. What does it mean by this? Okay, let's consider the two cases, two situations. Okay, when this object, or we call that when it's a body, but in science we call it this is a body. Okay, when this object, when this body is taken out, is removed from the furnace and is put in the surrounding with temperature of 30 degrees Celsius, there are two possibilities. There are two possibilities regarding the temperature distribution throughout the body. Okay, possibility number one is the temperature of the whole body remains the same, or we can say is uniform. Okay, meaning from the inside, let's say this is a copper ball. Copper ball at the center of the copper ball, and temperature at the surface of the copper ball almost the same. Meaning T center, okay, T center of the copper ball is similar as compared to the T surface of the copper ball. Okay, this is condition number one, whereby we say the whole body has uniform temperature distribution. Okay, so this is the case for a copper ball. And if the copper ball is small enough, okay, if it is a very big copper ball with a diameter of 2 meters, let's say, then the situation could be different. Okay, but if it's small enough, then we can assume, it is safe to assume the temperature at the center throughout the whole body from the center to the surface is almost the same. Okay, not the same, but almost the same. So we can say temperature distribution in this body is uniform. But let's consider another case, a roast beef. Okay, roast beef. Let's see. You put a piece of beef inside an oven, okay, to roast it. Okay. Then you measure the temperature, okay, of the beef after, let's say, 15 minutes. Okay, after 15 minutes. So this is what you get after 15 minutes. Okay, let's say the beef, yeah. So you will see at the, maybe not 15, 5 minutes lah, 5 minutes. Okay, so after 5 minutes of heating, so this is what happened. You see the surface of, the outer surface of the beef is at 110. If you go further inside, then it is at 90 degrees Celsius. And if you go reach the center, you measure the temperature, okay, the temperature, you found that the temperature is only 40 degrees Celsius. Okay, this is case number two, whereby we say the temperature distribution over the body is non-uniform. Okay, so you see there are two situations, right? So because there are two situations, that's why we have to use different method in determining the temperature of the body over time. Okay, this one I will explain further after this. But before I proceed, I want to ask you, what are the factors which lead to the difference? Why? What are the factors? Okay, because of what? What are the factors which determines the difference. What makes copper ball different as compared to a beef? I want you to tell me. Okay, because they have different what? Because they are different in terms of what? I give you half a minute to think. After that, I'm going to ask you to type your answer in the chat box. Okay, half a minute you think now. Start. Okay, because they have different what? I want your answer to be because beef has a different what as compared to copper ball. Or another case is, let's say if a small copper ball and a big copper ball, right? A big one might not have uniform distribution. Why? Okay, I want you to type your answer in the chat box. Okay, you type it now. Okay, type your answer now. Different heat capacity. Okay, CP, different CP. At different thickness. It could be, but this CP affects how much heat you can contain. See, it could be, but I need a more direct, yeah, can be more accurate. Your answer is not wrong. Okay, different heat conductivity, yes. Okay, different K value, right? Because conductivity determines how much heat is transferred throughout the body. Okay, good. Copper ball has higher thermal conductivity. Okay, good. Yeah, because different thermal conductivity. Any other factor? Any other factor? So far only 3 answers. I want more answer, guys. Different outer surface. Different outer surface. If your answer is outer condition, right? If your answer is outer condition, meaning the H value of the outer of the surrounding, that's the correct answer. Okay, fifth. Next, different composition. Different composition then leads to different what? Different composition then lead to, if you say different composition is too general. Okay, I will continue now. I will tell you the answer. Okay. Just now, some of you mentioned different K value, different H value, right? But you miss one, that is size. Size of the object, like what I mentioned, right? For copper ball, if it is small enough, then we can assume the temperature distribution is uniform. But if you have a very big copper ball, then the temperature distribution might not be uniform throughout the body. Okay, so size is the third factor. But before that, so now I want to introduce you a new property. Okay, it's called Bayes number. Okay, scientists developed this, okay, in order to check, okay, when we have an object, we can assume that object has uniform distribution, temperature distribution of throughout the body, or it has non-uniform temperature distribution. It depends on the value of Bayes number. If the value of Bayes number is less than 0.1, then we can safely assume that there is a uniform temperature distribution across the body. Okay, temperature gradient in the solid is small, just like copper ball, right? So this is just imagine. So this is outside, right? Then this is throughout the body, right? The cross section. So from the center to the surface, temperature is similar, almost the same. Okay, so let's say here is 70. Here is maybe 68, something like that. Okay, outside temperature is 30, right? So we say when the Bayes number is less than 0.1, then this is what we can assume. We can assume that the the body has a uniform temperature distribution across the body. Okay, because the resistance to conduction within the solid is much less than the resistance to convection across the fluid boundary condition. This one I will explain later. Okay, when the Bayes number is greater than 0.1, then we can say the temperature, the body has a non-uniform temperature distribution across the solid. So for example, the beef, right? So the inner temperature is, the center is 40 degrees Celsius. But at the surface of the temperature is at 110, okay, degrees Celsius after 5 minutes of cooking. Okay, at maybe in an oven of 200 degrees Celsius or 150. Okay, so this is how we determine, okay, which system a body falls into. Okay, next I want to explain more about Bayes number. Okay, Bayes number is dimensionless. Okay, for information, so meaning it has no unit. So it is a ratio of thermal resistance in the body, okay, compared to the surrounding. Okay, let's see. So it depends. So from here, from the formula, Bayes number equals to HLC divided by K. So what is H? H is the convective heat transfer coefficient. Okay, H, what you learn in convection. K is the thermal conductivity of the solid of the body. Okay, and X and LC is characteristic length. Okay, this LC, not X1, LC, sorry. LC is the characteristic length. What characteristic length represent the size of the body. Okay, it is a term used to measure the size of a body. Like what I mentioned, right? If the copper ball is very big, the diameter is 2 meter, as compared to a copper ball, the diameter is 1 cm, then the value of Bayes number is different. Okay, and LC, how you calculate, is the volume of the body divided by the total surface area of the body, V over A. Okay, so for cylinder, the value is R divided by 2. But for sphere, it is R divided by 3. You can try it yourself, right? Prove this formula. Okay, volume of sphere divided by volume of total surface area of sphere. Then you will get R over 3. Okay, if it is a cube, okay, x height also x, then what you get is what? LC equals to x power of 3 divided by 6 x square, right? So you will get x over 6. Okay, this is how you get the characteristic length, LC. Okay, so you see the bigger the length, then the bigger the value of LC. Then you see Biot number is directly proportional to H, directly proportional to LC, and inversely proportional to K. So what does it mean? So it means, let's start from K, most easily can be easily understood. When the value thermal conductivity is high, when you have a very high value, for example copper, right? The value of K is around 100, 200 something, right? 200 over copper. Then when K is great, is high, then your Biot number will be small, right? If you keep H and LC constant, then when you compare K for copper as compared to K for the beef, right? Of course, copper has a much higher thermal conductivity. So with both similar size and similar surrounding with similar H value, then it's very clear Biot number of the copper will be much smaller as compared to beef, right? Because K value of copper is much higher as compared to beef. Okay, so it's inversely proportional. Then what about LC? I explained already just now. If the size of the copper, right? If the size of the copper ball is 1 cm as compared to the size of copper ball is 1 meter, then of course LC is greater for the one with the 1 meter diameter. Then the Biot number will be bigger for this one, the 1 meter diameter copper ball. Then the Biot number will be greater. Then it has high chance that the Biot number can be greater than 0.1. Then we cannot assume the whole copper ball has uniform temperature distribution across the ball. Okay, then what happened to H? H is also directly proportional. What does it mean? It means, let's say you have this object, okay, copper ball. K is fixed, LC is fixed, okay, but two different conditions. Okay, condition number 1, condition number 2. Condition number 1 is there is no fan, right? There's no fan. So the copper ball is cooled under natural convection. H is around 20, right? 20 watt per meter square. Sorry, I per Kelvin, right? Okay, then as compared to a situation number 2, whereby you install a fan, right? So H is increased to maybe it depends. Well, it depends on the velocity of the airflow, right? So let's say increase to 200, right? 200. So it is 10 times as compared to the situation number 1. So what we will see is the value of Biot number will increase for 10 times, right? So that's why you have high chance that the higher Biot number will be greater than 0.1. Okay, why? This one, let me explain a little bit. Why when you increase the H, the Biot number will increase, then the body temperature distribution will become non-uniform. Okay, it is the terbalik, right, as compared to the K. When you have K, very high K, then heat can be transferred very fast. So you will have uniform distribution across the body. But when you have very high HR, when you maintain K, what will happen is heat will lose from the surface. You see, heat will lose from the surface to the surrounding very fast, right? Because when H is high, it means heat can be lost through convection very fast, right, to the surrounding. So it means temperature at the surface of the body will drop very fast, right? But if K maintain, then heat is the what do you call that? Heat transferred from the center to the surface not fast enough as compared to heat loss to the surrounding. Because now in this situation, you have airflow, so heat is lost from the surface to the surrounding in a very fast pace, right? But then the rate of heat loss is very high as compared to the rate of heat transferred from the center to the surface, right? So the rate of heat being transferred from the center to the surface is not enough, is not sufficient to compensate the heat loss to the surrounding because of high H value airflow. So it means over time, what will happen is temperature at the center will be much higher as compared to the temperature at the surface. Then you will not have a uniform temperature distribution over time. This is the reason. As compared to situation number one, where H value is very low, right? Then heat loss to the surrounding at this pace, and at the same time, the heat can be compensated, right? By conduction, right? Heat can be transferred from the center to the surface fast enough to compensate the heat loss to the surrounding, to maintain the temperature of the whole body at the same T. So under this situation, the whole copper ball can be assumed at the same T body. But in case number two, whereby you have very high H, then temperature at the center is much greater as compared to the temperature at the surface. Then under this case, situation number one, Biot number is smaller than 0.1. Under this situation, Biot number is greater than 0.1 because of H. Okay, you know H is directly proportional to Biot number. Okay, so let's proceed. So in determining the temperature of a body, now when we talk about transient or unsteady state, our interest is we want to know, let's say, if we cool this copper ball down, right? We want to know, let's say, initially it's 70 degrees Celsius. Okay, after 5 minutes, okay, after 5 minutes, what is the temperature of this object? Okay, then after 10 minutes, what is the temperature? So if I want to design a system to cool down, let's say copper ball is my product. Okay, I want to design a system to cool it down. Okay, I want to know under the cooling situation, how much time will be taken in order to cool the product from 70 degrees Celsius to 25 degrees Celsius, or maybe to 30 lah. Okay, so that I can pack it. If 70 is too hot for the worker to touch it, right? Not safe. So I want to know I need how much time in order to cool it down to the safe temperature so that workers can use their hand to touch the ball and take it into the box for packaging. So I need to calculate, right? Yeah. So, but there, I have mentioned, right? I've mentioned there are two possibility. One is outside is when outside temperature is 30, then inside also 30 because temperature distribution is uniform. But there is another situation like the beef. Outside is cold already, but inside still hot, right? So first we must determine your body falls under which category. Falls under uniform temperature distribution or falls under non-uniform temperature distribution. Okay, so after determining that, then we need to use different formula, different method to determine the temperature of the body over time. Okay, so the if sorry if the Bayes number is less than 0.1, this is this case. Then if the Bayes number is greater than 0.1, like the case of roast beef, then the temperature distribution is like this. So for the case number one, whereby there is uniform temperature distribution, we use lump capacitance method. But for case number two, like the case of roast beef, the Bayes number is greater than 0.1. We need to use another method. It's called graphical method. Okay, because under the first situation, we can assume the whole body has the same temperature, only one temperature. But for the case number two, there are many different temperatures because across the body, the temperature at different point is different. So under second situation, when you ask me, what is the temperature of the beef after 5 minutes? Then I will ask you one question. I will ask you, which part of the beef do you mean? But for case number one, I don't need to ask you this question because the copper ball's temperature is the same from the center to the surface. But it is not the case for the beef. Okay, so that's why we must use different method. So let's see the two methods one by one. Okay, for lump capacitance method, I mentioned already, Bayes number less than 0.1, and the whole body has a uniform temperature distribution. Okay, this is how the lump capacitance method equation is derived. It's based on energy balance equation. So we know that there is no heat in, there is no heat generation, right? Then heat is being released to the surrounding, right? Then this is the formula, right? This is, you see, heat is lost to the surrounding through convection. So that's why you see HA temperature difference, right? We assume effect of radiation is negligible. That's why you don't see heat loss through radiation, right? Mostly through convection. Okay. Then this part is actually MCP delta T, right? If you can see that, because rho V equals to M. MCP delta T. So start from this basic equation, then we move on, then we integrate both parts, right, over time. Okay, so boundary condition is when at T equal to 0 second, initial temperature, remember, because now Biot number is less than 0.1, so we assume T center is same as T surface. So there's only one temperature. So the whole temperature of the body is at T naught, right? But when T equals to T, right, the temperature it becomes T, right, or TT. Okay, and temperature across the body from the center to the surface is the same, one temperature only. Okay, because of that, we want to solve this by integrating both parts, right? So here is T naught, right? Here is T naught to T. Here is 0 to T, right? So you solve it, then this is what you get. Okay, this is the solution of this. Okay, so this is the formula you can use to determine the temperature of the body T at certain time or vice versa. Okay, so let's say, so this is the surrounding temperature. Okay, this is the initial temperature of, let's say, let's take copper ball. Initial is T is 70. Surrounding is 30 degrees Celsius. So this is T infinity, right? Then you want to know after 5 minutes, okay, after 5 minutes, what is the copper ball's temperature? Then you can insert T must be in second. So that's why you must times 5 with 60, 300 second. Substitute all this into this equation, then you will get what is the T after 5 minutes. Or vice versa. Okay, you want to know, let's say, I want to cool my copper ball to 30 degrees Celsius. How much time is needed, right? Then you know your T is 30, right? So you substitute 30, then you know the T infinity, you have the T initial, you have the H, you have the surface area, then you have the density, V is volume, Cp is heat capacity. You want to know the time, then you can determine the time needed to cool this copper ball from 70 degrees Celsius to 30 degrees Celsius. Okay, so vice versa. Then what if you want to know how much heat can be released, right? Normally this one is more useful, right? Okay, this is when you integrate, the whole thing, then you know the summation of the heat lost to the surrounding, right? Total amount of heat released. Let's say you say one copper ball, I cool it down from 70 to 30 degrees Celsius, right? Then 5 minutes, let's say 5 minutes, okay? Uh, no, time doesn't matter. I cool it down from 70 to 30, right? I want to know, with this cooling, how much heat is lost to the surrounding. Then you can use this formula to calculate how much heat is lost to the surrounding. Okay? And this is actually small q. This is if you want to know let's say at T equal to 10 seconds, at this 10 seconds, what is the heat loss rate to the surrounding? Okay, because we know under transient temperature, the Q is no longer constant. Okay, but so far before we enter into transient, the Q is constant because our assumption is the system is under steady state. So Q is constant over time. But under transient, Q changes over time. So when T equals to 10, Q is certain rate. When Q is 1 minute, Q now, and when T is 1 minute, Q also change. Is different over time. That's why we call that as transient or unsteady state. Okay, so this is the formula you can use. But for the case of, let's say, beef, right? Biot number greater than 0.1, then you have to use graphical method. Meaning you need to use different graph, right? You see different graphs, so many graphs. And they are graph for semi-infinite solid. They are graph for very big sphere. They are graph for very long cylinder. They are graph for very big plate. Okay, bear in me, I will complete this within maybe another 5 minutes. Yeah. Okay. So what is a semi-infinite solid? So you see, for semi-infinite solid, okay, I show you in overall first. So semi-infinite solid, this is the graph. Okay, let me explain first. This is the distance. This is the distance from the surface. Let's say this is a semi-infinite solid. Okay, then it is exposed to a surrounding with H, right? Certain H value and certain T value, right? T1. Okay, then with H, initially the whole solid is at T naught, right? Then this is a distance from the surface. Only the surface is exposed to the surrounding. Okay, so you are interested to know what is the temperature at this point, whereby the distance from the point is X. Let's say 1 meter from the surface after 5 minutes. Okay, then you can use this graph. Okay, you see the X axis is alpha. Alpha is K. Okay, K thermal conductivity of the solid divided by rho, density of the solid, and Cp, heat capacity of the solid. Okay, alpha, then distance, 1 meter, time, 5 minutes, right? Then you know the X, right? Then which curve to refer to is H, then this is refer to surrounding, H of the surrounding, time, alpha, and K. This is for object, right? Let's say you get 0.4. Okay, let's say your X is 0.8. So move to this, then you get, this is the value of your Y is, let's say 0.06 equals to T minus, what is your T original? T original is T naught, right? Let's say it's at 50 degrees Celsius and surrounding temperature is 20, let's say. Okay, so T minus, this is T naught, right? 50 divided by T1. T1 is 20 minus 50. So you can get what is the temperature at this point after 5 minutes under this condition. Okay, so same goes to large plate. Large plate is this. You see, okay, let me come back first. What is semi-infinite solid? Okay, let me tell you. This graph is actually derived from this equation. You see, this one is equal to this called error function. Okay, you can also use this formula to determine, but it's very long, right? So you need to use you need to refer to so many different table, or yeah. is a complicated, very tedious calculation. So that's why scientists come out with the graph. Okay, easier way, faster way for you to determine the y. Okay, and example of semi-infinite solid. Okay, for example, you want to know the temperature, let's say ground temperature. Okay, some country with 4 seasons, right? During winter, the air temperature can drop to, let's say, negative 20 degrees Celsius, winter, right? So the earth, the earth temperature, right? The ground temperature will also drop, right? But according to thickness, right? So that if you go very deep, then the temperature might be still remain at 20 or even hotter, right? Yeah, because the sand, the what do you call that? The earth, right? The ground is not a good. The K value is not very high, right? So this ground can be assumed as a semi-infinite solid. Okay. Another example of semi-infinite solid is a very thick wall. Okay, you have a very thick wall. The wall is exposed to H and T0, T1. Okay, surrounding temperature with certain convective heat transfer coefficient, right? And the other side of the wall is insulated. Okay, insulated. Heat is lost through one surface only, right? This part is insulated. So this thick wall can also be assumed as a semi-infinite solid. Okay, so what about a large plate? A large plate is like this. So you see, the heat is lost through two surfaces, upper and lower, or it can also be like this. A wall, right? A wall, but both sides of the wall, maybe this wall is like this, right? It's very big. We say large, right? Large plate, large wall, right? A wall with very big surface area, right? The thickness is finite, right? So heat is lost through both surfaces, right? But the thickness is finite, right? So the thickness is 2x. You see the thickness is 2x. 2x1, sorry, 2x1. So under this situation, let's say this wall is hot, then the highest temperature will be at the center. So heat will be lost from the center to the surrounding through the wall, right? So when you use this graph, then you will need to determine the x is calculated, is based on from the center. Okay, the rest are the same. Then you can determine the temperature. Let's say I'm interested in this point, okay, which is also 1 meter from the center. Or maybe if this wall is 4 meter, right, the thickness, then the x1 is 2 meter, right? If I want to know what is the temperature at this point, which is 1 meter from the surface, then I can do this. Same goes to, and this graph is for center only. Okay, you see this graph is at any point, but this graph, a clearer one, is only for if you want to determine the temperature at the center only, not any point. Okay, for long cylinder, the condition is it is very long, very long. So heat is only, we can say the heat loss through the both end, like this surface, you know there are two ends, right? If the cylinder is very long, then the heat loss through these two surfaces, two circle, is can be negligible, right? So heat is only lost through the cylinder surface. Then this is the graph we use. So X is counted from the center, right? Then you use the graph. And if you're interested in the temperature at the center of the cylinder only, then this is a better graph. Same goes to large sphere. This is the graph. And if you're interested in the center of the large sphere, this is the graph. Okay? So that's the end of this lecture. I'm sorry for overshooting. This is a general overview lah, on unsteady state. Actually, I have covered, I think 70% of unsteady state already for heat transfer lah. For mass transfer, I think we will share the recorded lecture lah by Dr. Nadia. This is a very short topic. Yeah, so it can be covered within a week actually. Okay, so in the next lecture, maybe next Wednesday, we will talk about, let's say, now you see all the object we consider are big, large, right? Are large. Okay, so basically we neglect the heat loss through like the two ends, right? But in some cases, let's say the cylinder is not so-called very long, very large, right? Then you have a finite cylinder. For example, meaning heat loss through these two surfaces are significant. Let's say this is the length, the diameter is 1 meter, the length is 1 meter. Then because it's not long, very long, right? Then meaning the surface area of the two circles of these two surfaces are significant. So you cannot neglect. You cannot assume the heat loss through the two surfaces are negligible. You must consider the heat loss through these two surfaces, besides the heat loss through the cylinder surface. Then this one is more complicated. You need to combine. It's a multiple, like you need to consider heat loss through this and also consider heat loss through the two surface. This one is more complicated. You need to combine your Y. You need to have Y cylinder, long cylinder plus Y of heat loss through the two surface. These two surface can be considered as large plate. So this one I'll explain in the next lecture, next week. I think can be completed within 1 hour. Okay, for your information, final exam covers all this. Okay, there is one question. The weightage of the question is 30%. So make sure you learn this topic well. Okay, so before we end, is there any question? Any question on this? So on test 1 will be test 1 pula. Test 2 will be next Monday, right? Test 2 will be next Monday, 4:30 to 6, right? So what we are going to do next Sunday, I think we can use that time for some revision, for you to ask question, so that you can be more prepared for the test too. Then next week on Wednesday, then we can complete the second part of the unsteady state. Then the whole course can be considered completed. Yeah, then the last week, we can use it for revision, for your preparation for your final exam. Okay, if there is no question, then we can end here. Thank you for your time.
Thank you, Doctor.
Okay, welcome. Okay,
Thank you, Dr. Lai.
okay, welcome.
Thanks, Lai.
Welcome.